All right, let's dive right in. Today, we're pulling back the curtain on an architecture that could totally reshape how our cities move. And I'm not talking about some far-off theory. This is a real-world blueprint for using generative AI to manage city traffic, making split-second decisions when it counts the most.
So to get us started, I want you to think about this question. How does a city's traffic system actually think? We tend to imagine a smart city just predicting a traffic jam before it happens. But what if I told you that's only half the battle? The real magic isn't just seeing what's coming, it's deciding what to do about it.
And that, right there, is the heart of what we're unpacking today. The secret isn't just about prediction, it's about decision. It's all about building a system that can reason, that can choose, and that can act, all while under incredible pressure and never, ever compromising on safety. So here's our game plan for this explainer. First, we're going to nail down the system's main goal, control. Then we'll do a little surgery on the traffic brain to see all its parts. After that, we'll follow the data on its journey from a simple sensor to a traffic signal, pinpoint the exact moment of decision, and then, finally, see how the system acts and gets smarter over time. First things first, the goal is control. Look, before you even write a single line of AI code, you have to define the mission. For something managing critical city infrastructure, this is absolutely non-negotiable. An AI without a clear objective is just spinning its wheels, which is inefficient at best and, frankly, dangerous at worst. Now, what's really fascinating here is just how specific these goals are. The system's job is to minimize queue spillback, when traffic from one intersection backs up and blocks another one. It needs to make your commute more predictable, not just faster. And it has to juggle all of this on multiple timelines, thinking seconds ahead and hours ahead, all while sticking to the absolute letter of safety and policy rules. And let me be super clear on this point. The AI is a powerful advisor, but it is not the boss. It can suggest extending a green light to clear up traffic, sure, but it can never break the hard-coded safety rules. Things like making sure pedestrians have enough time to cross or giving an ambulance a clear path. Those are sacred. They're built-in guardrails that AI simply cannot cross. Okay, so we know the goal. Now let's see how the system is actually built to achieve it. Section 2, the anatomy of a traffic brain. We're about to pop the hood and look at the end-to-end architecture that makes all of this possible. And right away, let's just bust the biggest myth out there. The GenAI in this system is not a fortune teller. It's not the part that's predicting the jam. Think of it more like the strategist, the decision intelligence layer. It takes the predictions made by other models, weighs them against all the rules and what's happened in the past, and then it picks the best move. You can really think of this system in two halves. The first part is like the brain's senses and instincts. You've got this flood of raw data pouring in from everywhere: CCTV, GPS, radar. Then, specialized models chew on all that data to forecast what's about to happen, like changes in traffic flow or the chance of an accident. This is the system's gut feeling. Then you have the second half, which is all about reason and action. The GenAI decision engine is the rational mind here. It gets those forecasts and makes a choice. But, and this is so important, that choice doesn't just go straight out. It first has to pass through a safety gate for a final check against all those hard-coded rules. Only after it gets the green light is the command actually sent out to the signals. Okay, let's zoom in a little closer on the data itself. Section 3, from sensor to signal. We're going to follow the first 4 steps of the data pipeline and see how all that messy, raw information gets cleaned up and turned into something the AI can actually use. So it all starts with just sucking in raw data, like how fast cars are going. Then, simple rules spot important events, like, hey, this line of cars is getting longer. Next, that data gets bundled into feature windows, basically calculating things like the average speed over the last 30 seconds. And finally, standard machine learning models use those features to predict what might happen soon, like the risk of a spillback. And this brings us to an absolutely critical design principle. GenAI never sees the raw sensor data. And that's not by accident. It's a very deliberate choice. You want the AI to get clean, processed, context-rich information, not a chaotic fire hose of numbers. This lets it focus on one thing and one thing only, making the best possible high-level decision. And that brings us to the main event, Section 4, the moment of decision. We've seen how the intelligence gets cooked. Now let's watch the instant that choice is made, double-checked, and sent out into the world. So, step 5, that's the GenAI engine thinking through its options. Step 6, the all-important safety gate, our final checkpoint. Step 7 is control execution. This is where the digital command becomes a real-world change. And then step 8, the feedback loop. The system watches what happens and learns from it, which is how it gets better and better over time. So how do you actually ask an AI to make a call like this? Well, you use a very, very structured prompt. Look at this thing. It's not a fuzzy question. It's a direct order. It gives all the context, congestion, rules, past results, sets a clear time limit, and demands a specific output, even asking for a justification and a backup plan. And in return, the AI's answer is just as structured. It doesn't write a paragraph explaining its thoughts. It gives back a clean, simple, machine-readable JSON file. This is so crucial because it makes it incredibly easy for that safety gate to instantly read it, understand it, and validate it. No ambiguity, just data. Okay, enough with the theory. Let's move from the pipeline to the pavement. Section 5, action, feedback, and improvement. How does all this actually play out during a real traffic incident? This is where you really see the power of the whole system. When an incident happens, it's detected in under 10 seconds. The entire decision process, including the GenAI's reasoning, happens in less than 30 seconds. And a real-world fix like changing the lights or updating signs is in place in under a minute. I mean, that is just unbelievably fast. So how does it pull off that kind of speed? By being smart about where the thinking happens. The really time-sensitive stuff that needs to happen right now, like spotting a backup or flipping a light, happens on edge computers, right there at the intersection. But the heavy lifting, the deep thinking, like prediction and GenAI reasoning, that happens in the cloud, where you have all the horsepower you could ever need. And you know, to make a system this complicated actually work, you need absolute clarity on who's in charge of what. This ownership contract lays it all out. Engineers own the data and the safety rules. GenAI architects own the prompts and the decision logic. And some things, like metrics and rollbacks, are a shared responsibility. This isn't just about technology, it's about teamwork. And that really brings us to the single most important takeaway from all of this. GenAI is not here to replace traffic engineers. Its real job is to be the missing link, the piece that connects a prediction to an action, all while playing by the rules set by human experts. It's an incredibly powerful tool in the toolbox, not a replacement for the expert. So I'll just leave you with this question, because it really gets to the heart of building AI you can trust. If a system can't explain why it did something, if it can't undo its mistakes, and if it can't learn from them, is it really ready for the real world? This architecture shows us a path forward for building systems where the answer to that is a confident yes.